Hello there, this is Professor Eckhouse. I'm going to talk about functions and their notation today. So what is a function? So here's just a little graphic of a function machine. So a function is basically a machine. It's something that has an input and an output, right? So if any sort of function like a car, you put the gas in, you get the energy out. So in this picture here, we've got some spheres going in and some cubes coming out. So the function does something inside there to convert them. So the same thing is happening to a function. The numbers go in as one thing and they come out as something else consistently. So the function does something similar to every single input and creates an output. Okay? So some key terms to know before we get into the details is what is a relation? So it's a set of ordered pairs, and remember that an ordered pair is something like this, x, y. So a relation is going to have usually some sort of a set sign around it, and then a bunch of ordered pairs. So I'm just kind of throwing some random things in here, nothing that you need to really see a pattern in because I'm just making it up. That's a relation because I have basically said it is. Okay, it's a set of ordered pairs, right? And it can come from a function, or I can basically just say, here's my function, here's my points. That's kind of the simplest thing we could talk about. All right, so let's talk about what a domain is. So let's look at those numbers there also and think about what is the domain of that relation right there. So the domain is the input value. The x value is considered the input, and the independent variable is also what it is considered. Okay, so the domain is the input, the x value, the independent variable. It's the first value in the ordered pairs. So the domain is the first number when we have a set of ordered pairs. It's the x value. All right, so let's move on. What is the range? So the range is the output. It's the y value, it's the dependent variable, and it is the second value in the ordered pairs. So we'll make the range green. So this is the range. Those numbers make up the range. Okay, the second value in the ordered pairs. All right, a little bit more. A function is a relation that assigns a single value in the range to each value in the domain. A single value in the range. So no x values are ever repeated. And if you repeat them, it is not a function. Each possible input value leads to exactly one output value. The output is a function of the input. Okay, so we've got, let's just make sure you really see this. Each possible input value leads to exactly one output value. That is super important. All right, so let's look at some examples of this. So determine the input and output of each of the following, just real life examples. All right, the distance you drive in a certain number of minutes. What's the input? So you've got to think, we've got distance and we've got minutes, which is time, right? That's time. So which one is the input? Does the distance depend on the time that you've been driving, or does the time you've been driving depend on the distance? So in this case, the input is time in minutes. It could be in seconds, it could be in hours, but it's in minutes, it says. All right, the output is the distance. So if I keep on driving, I'm going to go farther, right? All right, the next one, the pay you receive for the number of hours worked. So let's underline the two parts, the pay and the number of hours worked. So which one is the input? Pause the video if you want to think about it, but time is the input in hours. And the output is your pay in most likely dollars, okay? So time in hours. So I just want to point out here that time is always the input. Time doesn't depend on anything. Time is independent of all things, right? So it's always going to be the input. So anything with time in it is pretty straightforward. All right, so let's look at the height of a stomp rocket. The height a stomp rocket goes into the air. So height, and it doesn't say anything. There's nothing else to underline. So what's happening with a stomp rocket? You're stomping on it, right? So it's not always going to say everything very clearly, but the height is going to depend on the force of the stomp, right? Force of the stomp. So think physics here. The force of the stomp is the input, and the output is going to be how high it goes, the height. Okay, so it's not always in the sentence. You got to put a little thought into it. All right, the last one. The proceeds from a concert. Every ticket is the same price. So think about this one for just a moment. Pause if you need to. So what depends on what? You're selling tickets, you make some money. All right, so the input is going to be the number of tickets you sell. The number of tickets sold. All right, and the output is going to be the proceeds. What does proceeds mean? Well, it means the money made. Okay, so there's more examples in the ebook in the first section. Okay, so let's move on to determining whether a relationship is a function or not. All right, so the first one is this one right here. We've got some inputs, right? And they lead to some outputs. So we've got, this one going, P going to M. We've got Q going to N and R going to N. Is this a function? And the answer is yes. And if that confuses you, just hold tight. We'll talk about it in just a second. The next one, every single input leads to a different output. So yes, this is definitely a function. The last one, we have P going to X and Q could lead to Y or Z. So up here, we said that each possible input leads to exactly one output. So how many outputs does this one have? Well, it has 2. How many outputs does this one have? It has 1. How many outputs does R have over here? It also has 1. It happens to be the same one as Q, but each input has 1 output. Okay, so this one is no over here on the right because this Q leads to 2 different outputs. All right, so just a quick set of definitions here. The domain is the set of all possible inputs. The range is a set of all possible outputs. A function is a relation in which each input has exactly one output, and an ordered pair looks like that, input, comma, output. Okay, so everything kind of summarized right there for you. All right, so example 2. From the following tables or ordered pairs, determine the domain and the range and state if the relation is a function. Okay, so these problems take just a little while to do, so bear with me. All right, so the domain. The domain is the input. So the domain is 0, comma, -2, comma, 4, comma, 9, comma, 6. The range is the outputs. So 2, comma, 1, comma, 2, comma, 1, comma, 2. So I could do that, or really, I could list them just once, 1 and 2, but I'm going to list them all. All right, so another way, I'll just put it right here, the range is just 1 and 2. Okay, so that's also an acceptable way to do it. All right, so we've got 0, -2, so this is domain right here, 4, 9, and 6. In the range, we've just got 1 and 2. All right, so 0 leads to 2, -2 leads to 1, 4 leads to 2, 9 leads to 1, and 6 leads to 2. All right, do any of the, and this is the range over here, I forgot to put R for range. Do any of the domains, any of the values in the domain lead to both 1 and 2? No, they don't. So every single item in the domain, every single value, only leads to one thing. None of them have 2 arrows going from them. Okay, so yes, this is a function. All right, so you try number 2, or part B. Pause the video and give it a try, and I'll give you the answer. All right, so there's the domain. The range is 2, 5, 7, 0, and you can say 5 again, but you don't really need to. All right, so the domain we'll write right over here in the purple. The domain is the purple one. So we've got 2, 3, -1. Well, we don't need to write 3 again. We already have it there. And 4, oh, that's going to be the big clue there. There's 2 3s listed in the domain. So let's see if they go to 2 different things. All right, and then the range is 2, 5, 7, 0, and 5, which we already have. All right, so let's look at the first one. 2 leads to 2, 3 leads to 5, -1 leads to 7, 3 leads to 0, and 4 leads to 5. This is not a function. No. Why not? It is because of this one right here. That's why. Because 3 leads to 2 things. It's okay that 2 things lead to the 5 on the right side, because that's not the definition of the function. What we're worried about with the definition of a function is that every input leads to only one output, and 3 right here leads to 2 different outputs. All right, one more. Why don't you give this one a try? And it's written a little differently, so you have to find the domain as all the x values, and then the range is all the y values. All right, so the domain is 2, 3, 4, 5. And the range is 3, 5, 9, and 12. And you might see it already, but I'm going to go ahead and write this down. The domain is 2, 3, 4, 5. And the range is 3, 5, 9, 12. All right, so 2 leads to 3, 3 leads to 5, 4 to 9, and 5 to 12. So yes, this is a function. All right, so let's move on to the next topic. Actually, not yet. Let's summarize this. Determining whether a relationship is a function. Identify the input values, that's your domain. And then identify the output values, that's your range. And then read this last thing. I'm not going to read the whole thing to you, part 3. All right, so that summarizes what we just did. All right, so function notation is the next thing we're going to look at. And this is very important for everything you do in math from here on and forever. So very key, basic, foundational skill. So practice this a lot until it really makes sense. All right, so y equals 7x minus 3, when we use function notation, becomes f of x equals 7x minus 3. Right? So the variable y is replaced with something that gives us more information. So now we can differentiate between equations that aren't all called y equals. So now we can have f of x and g of x and h of x and c of x for cost and things like that. Okay? So we usually use, just to make that clear, we usually use f of x, g of x, h of x, but we can use others. But those are the most common ones that you'll see. Okay, so how to use function notation in word problems. So cost with respect to number of tickets sold, like we talked about just up above. So you've got to decide what is going to be what. So let's say C is going to be cost, all right? And N is going to be number of tickets sold. And I usually and this is where things get hard for people because you can make up your own stuff, and that's a lot of people get lost with that. So use letters that make sense. C is the cost, N is the number of tickets sold, okay? So now the way the function notation is going to work is we're going to say, well, cost depends on the number of tickets sold, okay? So the number of tickets is going to be the input, and this is important, and this is going to be the output. Really important to decide which is which, okay? So now we're going to say C, the cost, is going to depend on N. Okay, so here we put the output. It depends on the input. What you get as an output depends on the input. Cost is a function of the number of tickets sold. That's how you would say that. Cost is a function of the number of tickets sold. All right, next one. All right, distance with respect to time driven. So distance is going to be d, okay? D is distance. and we're going to call t time. Okay, so we've got distance, we've got time. All right, so which is our input and which is our output? All right, so input is time, always, and output is distance. So just think logically, like use common sense. What depends on what? Time is always the input. Okay, if you have time in the problem, always the input. Okay, so this we're going to write d as a function of t, where d is the output and t is the input. We put a t in to the function. And so we're going to say distance is a function of time spent driving or whatever. Distance as a function of time. All right, next one. Income dependent upon time worked. All right, so we've got income and time. All right, so we'll say, you could say pay for P for pay, or I'm going to use I just because the word is income. So that way we can keep track of what we're doing. Income, and you can use a small or big, it doesn't really matter. And T equals time. All right, so think about which one is independent and which one's dependent. Which one's the output and which one's the input? What do you put in? Well, time, again, is input, always. Output is the how much you make. Okay, you work and then you make some money. All right, so what is this going to look like? It will look like I as a function of time. Income as a function of time. All right, so again, this is the output and this is the input. So I'll say it again. Income is a function of time spent working. You can continue like that. Income is a function of time spent working. All right, so try this one. Represent height as a function of age using function notation. All right, so let's rewrite this in English. Height is a function of age. All right, so let's change height to h. H is a function, we'll use f, of age, a. So height is equals, right? So height is a function of a. So output is a function of input. So output is a function of input. All right, try the next one. So write a formula for perimeter of a square as a function. So all we do with these, because we were already given the equation, so let's do number one. P equals 4s. So perimeter equals 4 times the length of the side of a square. That's what that means. But when we start using function notation, we're going to say perimeter depends on s. Okay, so P dependent upon s. S is the input. P is the output. So it looks like that. That's all you do when you're, especially when you're given letters like this, is you can just put the independent variable in here to show that you're finding perimeter with respect to s, which is the length of the side of the square. So try this one. A equals L squared. So the area of a square is equal to the length of the side squared. All right, so they changed from S to L just to keep you on your toes because you're going to see both. All right, so you've got to be flexible. S could be the length of the side. L can be the length of a side, so either one. All right, so A with respect to L equals L squared. The area with respect to the length equals L squared. Another way to say it is area as a function of the length is L squared. And number one, perimeter as a function of the side of S is 4s. All right, general note on function notation. We read y equals f of x as y is a function of x, right? Y is a function of x, sorry. The letter y or f of x represents the output value. All right, so let's try another one. A function n equals f of t, where n represents the number of homes sold in Vermont in a certain month. What does f of 5 equals 251 represent? What does that represent? Well, n is the number of homes sold in a certain month. So t, time, is months, right? This is months. So what do you think 5 stands for? Well, I think 5 stands for January, February, March, April, May. May is the 5th month. All right, and this represents n. This is n, right? Equals the number of homes sold. All right, so it represents, so in May, month 5, 251 homes were sold. All right, so there are 2 videos in the ebook if you need more help on this, 2. So, because this is kind of hard, and there are 2 very different examples. So I would highly recommend going into the ebook and looking at this section on function notation. You can find that in Lumen under section 4.1. All right, graphs of functions. We're going to look at a few different functions here. And so remember we say y equals f of x. Y is a function of x. Okay. So then xy becomes a graph. Okay. So we're going to look at some graphs of some functions. So let's look at, I'm just going to put them on here and then I'm going to erase them, okay? So you're going to have to just kind of watch. So what is that? Is this a function? So if we take this and we think about it as every x has to have one y. Does every x have one y? And it does on this one, okay? And we're going to look at using that vertical line here in just a second. So that one is a function. All right, what about this? Is that a function? If you found an x value, does it have one y in every single case? Well, this one's just a little bit harder to think about. So here's a good way to think about it, is called the vertical line test. So I'm going to grab this. I'm going to try really hard to grab this thing right here, and I don't know if it's going to let me. All right, so imagine I was able to grab this, this arrow right here, and I'm going to take it and scoot it over and put it on top of this. And I'm going to draw a line instead, a vertical line, there, 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 there. No matter where I put it, it's only crossing my graph one time. Okay, so if it only crosses it one time, it means for every x there's only one y. And so it is a function. So that graph right there is a function. Okay, so let's get rid of that. What about this? It keeps going. If I could take that vertical line and scoot it across, would it ever cross through twice? No, it would not. So no matter where I draw the line, it only crosses through one time. If it crossed through twice, it's not a function, but this is a function because it only crosses through one time. There is only one output for every input. All right, so what about this? All right, so right here it's fine, and right here it's fine, but right here it is not. So it is not a function. Even if just one place, it has more than one place where it crosses. That means for this value of x, I have this y, and this y. I have 3 of them. So it's not a function. All right, what about this? Definitely not a function. All right. What about one more? What about a circle? What a circle? Nope. Every time I drew a line in this direction, it would cross through twice, every place. So that's not a function. All right, so that's how you determine if a graph is a function or not. All right, so how could we use the vertical line test to see if a set of ordered pairs is a function? So what you want to do is you want to graph each one. So I'm going to go 2, 2, and I'm going to go 5, -4, and I'm going to say -3, -1, and 2, -3. All right, so if I was able, I'm going to try one more time. If I was able to take this vertical line and move it around on, oh, look at that, it's going to let me move it around. No, it's not. On this graph, then it would go right through here, right? It would go through twice. So that means this set of ordered pairs is not a function. Another way to think about it is to say, oh, look, there's 2 2's that are the input. Do they lead to 2 different things? They do. They lead to a 2 and a -3. Okay, so either way you look at it, it is not a function. So the answer is no. All right, how do you say f of x? That's how you say it, f of x. F of x. So how would you say each of these, and what do they mean? So this one I would say f of 2. And what it means is you plug 2 in for the input, where x would go. Okay? F of b. That's how you would say that, f of b. And that means you would plug b in for the input. Everywhere you see an x, you replace it with a b. And this one you would say f of x plus 3. So you plug x plus 3 in for the input. Everywhere you see an x, you replace it with an x plus 3, which always is a little weird, but just think x plus 3 is going to replace any place the input is. All right, so let's do example 7 through 11 are all very similar. So given f of x equals 6x minus 3, find f of 2. Okay, so remember how to say this, f of 2. All right, so we're going to say f of 2 equals 6 times 2 minus 3. And get in the habit of starting like this, f of 2 equals. New habit. It's a good one. It's correct notation in math, all right? So we'd say 12 minus 3, and that is 9. All right, so you try 8. And if you'd like to, you can go ahead and try 9. All right, so now I will do it. So f, oops, this should be a g. So that means nothing. Finding f of 5 means we wouldn't do anything because that's g. All right, so that's a mistake. So g of 5, find g of 5. All right, so I would plug 5 in every time I see a g, so every time I see an x. So 5 in every time I see this x right here, which is right here. All right, so 2 times 5 plus 4. That is 10 plus 4, which is 14. Okay, so g of 5 is 14. All right, given h of x is this, 3x squared minus 2, find h of negative 2 and find h of 0. All right, so h of negative 2 equals 3 times negative 2 squared minus 2. All right, 3 times negative 2 squared is 4 minus 2. That's 12 minus 2, which is 10. All right, h of 0 is 3 times 0 squared minus 2, which is just going to be 0 minus 2, which is negative 2. All right, what if the input is a variable? The process is the same, but the answer will have a variable in it. That's important to know. If your input is a variable, your new input, the answer will just have a variable. You just have to simplify it. All right, so given f of x equals 4x squared plus 3x minus 2, find f of a. All right, that just means every time we have an x, we replace it with an a. Okay, plus 3 times a minus 2. And if I didn't put the parentheses in there, I would just be done. But I'm going to simplify it without the parentheses. So 4a squared plus 3a minus 2. That's it. Okay, nothing else to do. All right, so given g of x equals 2x minus 1, we've got g of, now we're going to do g of h plus 1. All right, what this means is, make sure you've got this really clear. H plus 1 is going to go in where the x is. Okay, so where this x is right here. All right, so g of h plus 1, always start like that, equals 2 times, now I'm going to put in the h plus 1 where there was an x, minus 1. Now we do need to simplify this. So we get 2h plus 2 minus 1. So that is, now keep going, 2h, 2 minus 1 is 1, 2h plus 1. Okay. So I think that is the end of this video. Thank you very much for watching.